Good morning, everyone. I hope you have practiced or looked at the numericals that were done in the previous two classes. Coming back to what we were looking at with respect to self-purification in streams, we have seen that any stream where a pollutant or a contaminant is added as liquid waste into the stream or river, it goes through, or the stream goes through 4 zones of what we call as zones of purification. The first one is called as the zone of degradation. Then you have the zone of active decomposition. The next one is zone of recovery. And last, you have the clear or zone of clear water or clean water, where most of the pollutants have been removed. And we have seen that under each of these cases, we see the types of, or the changes that happen with respect to the conditions of, say, solids in the water, the type of organisms that are present, and the nature of sediments or sludge deposits that happen at the bottom of the stream during these phases. So we have looked at zone of degradation, zone of decomposition, zone of recovery, and we have the clear water zone. So these are the 4 zones that the stream, pollution, zones of pollution that happens when a stream is or gets pollutant or contaminant as a waste stream, which is entering the waters. Now, we always talk about certain indices or indications of self-purification that is happening in the stream or river. So we know that self-purification is a term that we have been trying to understand, that the stream by its natural processes is getting its water repaired so that it is able to reach its original state. So the stage of purification process has or involves physical, chemical, and biological factors. And if we are able to test these factors, we will be able to identify or find out or analyze these physical, chemical, and biological factors. We will be able to find out the exact condition of the water in the particular stage. So during these conditions, the stages, you can see that a river or a stream will be going through various phases. So the stage of purification, there will be physical, settlement, sludging, chemical, some oxidation, reduction, all those processes. Biological is definitely the organisms, the type of organisms that are acting, type of organisms that are present in the water, both. So all these things can be very easily understood by this figure here. So I want all of you to take a close look at the figure, the zones of purification. Okay, so initially you imagine the river to be having clear water, and you are inputting your waste stream. I hope you can see the cursor at this point. Okay, so what is written on the top is the zones through which your water or the river is going through because of the input of pollutant or contaminant at probably this phase. So where the water is clear, suddenly you're entering. Now you can see that a graph is put. This graph is very important because it is going to come to you as a separate graph. In this, they are calling it as how the variations happen within the zones of pollution, but this is also relevant in terms of what is called as the oxygen Sag curve, or how the oxygen which is present as DO in your water varies, and it's a very important concept. So if you look at this, you can see that when the water is clear, okay, in a river or stream, you are expecting it to have saturation level of DO. Okay, saturation level DO meaning the maximum quantity of DO that can dissolve in that water, but there DO is always with respect to temperature. So whatever temperature your water is having, that for that temperature, what is the maximum dissolved oxygen that can be present? It is very much dependent on temperature. And you know that if you are heating or boiling your waters or heating waters, we are actually giving out the oxygen from the water. You lose the oxygen content in the water. So higher the temperature, the DO is going down. So in the initial stages, we are assuming that there is 100% DO with respect to that temperature. That is a secondary part of it. Now, you look at the zone of degradation. So I'm first talking about the first part of this with respect to the DO only, and in connection with the 4 zones that the river is going through. So in the first case, you will see that the DO is 100% saturated, and then you can see the line dipping like this. So that means in the zone of degradation, as the degradation process starts, there is depletion of oxygen happening. And if you see this line here, it is indicating 0, DO of 0. So by the time the degradation has started and the stage of active decomposition is reached, the DO in the waters can go almost to 0. Then there will be a stage where your river is recovering or the stream is recovering, wherein slowly as the degradation or the organics are completely stabilized, then there will be reoccurrence of the dissolved oxygen in water. And you know what are the responsible things for giving out oxygen to water? Your algae, phytoplankton, etc. In the daytime, they will give out oxygen. Understood? So this, and even as the river flows, when the pollutant contaminant is less, the river flows, the currents, everything which are present in the water will allow for DO to dissolve. And since the organics have been decomposed here, they are not getting used up once again. And that is allowing for this recovery to happen. So you can see that the graph goes back, and by the time you reach your last zone, which is the clear water zone or cleaner water zone, whichever way you'd call it, you are already getting back to the initial stage of DO. Okay, so 4 zones of purification explained with respect to the dissolved oxygen. Now, you can have indicators which are physical in nature, like in the case of your clear water. Suppose you have a river where right now there is no pollution. The clear water will be present. There is no bottom sludge. The water will be free of color of any form. Once you have introduced your sewage directly, or whatever manner you have introduced it into the river, you will find a lot of floating solids, bottom sludge, because some of these solids will be heavy and they will settle down at the bottom of your river or stream or whatever it is, and slowly the color of water will start changing, and you will see that the water is getting murkier and turbid. Understood? So with respect to that, you will see a change. When you pass from degradation to active decomposition stage, you will see that the water gets darker and grayish. That is because of the active decomposition that is happening. Okay, the change of color will be very predominant. You will have gases. And like I told you, please keep it in mind. Whenever aerobic decomposition is there, we expect only 2 end products, carbon dioxide and water. But when you have too much of solids, the top layers may have aerobic decomposition happening, but whatever is happening in the lower layers will be anaerobic. And whenever there is anaerobic decomposition, your end products will be gases like methane, hydrogen sulfide, etc. And a lot of sludge coming to the surface, and it will form a sort of scum. You have probably seen this in most of our flowing streams, which are getting completely infiltrated or allowed to be used as disposal parts for your wastewater effluents. So in such places, you always see a sort of frothy, scum-like layer getting formed on the surface of the stream, because there is hardly any activity of penetration of sunlight or activity of organic decomposition, which is aerobic in nature. And because of that, you will get a lot of this scum appearing at the top. As you pass slowly from the active decomposition to the next stage of recovery, you will see that most of the top layers of water starts becoming clearer and clearer, and you will have turbid particles at the bottom as sludge. And from there, the bottom sludge also starts, getting decomposed, eaten away. By the time, your higher fish forms and things like that will be there. So they will also eat away into those materials, and you will probably having a clear bottom without much bottom sludge. You can also look at various types of, fish forms or aquatic forms, which will be able to survive and be present. So initially you have all types of fish and all. After that, when the degradation starts, some of the sensitive types will completely disappear. Okay, even the mollusk and algae and other type of plankton, they remain very few. There is a stage of active decomposition where almost all your aquatic fish and other things will completely disappear. Some bottom insects, what we call as worms and things like that, they may remain in the water. Other higher life forms will completely disappear. Slowly, as you start recovering back, you can see that tolerant fish or fish which will probably be able to survive in little not so fresh waters. Okay, they start reappearing back. Some of the mollusks and other things start reappearing back. And then finally, when you are getting a clear water, you will get back to a situation which is to your first level or nearing to your original level. So when you understand self-purification, it is associated with zones of pollution. It is also associated with the reduction in DO, change in physical and biological life within your stream. It is very, very important for you to understand that. And without that, whatever we are talking about here will become meaningless for you. Okay. So this is the first part of your self-purification and your zones of pollution. Now comes your very important oxygen sag curve. So if you look at this part of the curve, this is actually what is the way in which your oxygen depletion is also happening in the water. So oxygen sag curve is a very important term with respect to how the DO in waters are varying when you are adding a waste stream. Okay, now let me explain this curve to you first. On the x-axis, we are talking about the flow with respect to the time of flow within the stream in days. And on the y-axis, we are having what is called as the DO content in percentage they have put it. So on the top, they have given you the line for saturation DO. Again, I repeat, the saturation DO will depend on the temperature of water. And when I was telling about your syllabus, I told you we have a very big and very important equation called as Streeter-Phelps equation, okay, which is giving you at what time, when you are actually disposing a waste into the stream, by what time and at what distance from here will you be able to reach a level of certain DO in water, etc. So all that, the calculation part of it and all actually comes a little bit later. So right now we are not going into that, but here you have the time of flow in the stream in days on the x-axis, DO content in the y-axis, and the top horizontal line gives your saturation DO. So at a particular temperature, we can expect a saturation DO of, say, sometimes 14 milligram per liter. 14.6 is the maximum saturation DO, they say, at the lowest temperature of 0. But if the temperatures are coming to 20 or 20 to 30, we may end up with 10 milligram per liter. Then at that time, yeah, that will be the saturation DO. So what I want you to understand is the saturation DO for any water will depend on what is the temperature of that water at that particular time. So based on that, you will be having the saturation graph. Now, the oxygen Sag curve is also called as oxygen deficit curve. At any point when the self-purification of the stream is happening, you will have a saturation possible or a saturation DO possible and the actual DO. So here you can see this is the initial DO present, okay, and you can see they put an arrow here to indicate that it is at this point where they are discharging. So at the point of discharge of the waste, you will have an initial DO. Okay. Now, at any particular time t, and we have seen from our previous thing that oxygen will go down when the degradation is happening. So, after you have added the pollutant, there is no way this graph is going to go up. I'm talking about this graph, which is the oxygen Sag curve. Okay. So, initially at a particular point where you are disposing the waste, you will be having an initial DO. And when a time elapse has happened, here suppose we are taking as t, there you will have a DO present at that particular time. And at any point of time during the self-purification of the self-purification process or the zones of pollution, the difference between the saturation DO and the actual DO that is present there is called as oxygen deficit. So saturation DO. So I'll tell that with example. Say the water temperature is around 25 and your saturation DO at that temperature is, say, 10 milligram per liter. Okay. So initially, suppose at the point of application, we had around 8 milligram per liter. Okay. And because natural action will always be there in the river. So we cannot imagine that saturation DO at every point of time, nowhere we will show that the graph will be touching saturation DO, because this is a natural environment and there will be some contaminant getting added or some plant getting decayed that will get acted upon. So that's why we never have this DO starting from here. Don't make the mistake of putting your initial DO from the zero origin point. It cannot happen because initial DO will never be the saturation DO. Okay, so that's something that you people should be very careful when you draw the graph. So suppose there you had about 8 milligram per liter. Okay, so I'm telling for the temperature of what was there in the water at that time, saturation DO is 12 milligram per liter and your initial DO is around 8. And at that point, when you have added wastewater or organic material has entered into the water through your waste, there will be a depletion. And suppose you say at this point you have a DO of around 6. Then your DO deficit will be calculated as 10 minus 6. So that will give you the DO deficit. So DO deficit is defined as the difference between the saturation DO and the actual DO at that particular point of time. from where the pollution has entered into your stream. So, the normal saturation DO for fresh water, this you have to keep it in mind. Today, when you study it itself, it should go into your head that the normal saturation DO for fresh water depends on temperature, and at 0 degrees Celsius, you have the maximum saturation of DO of 14.62 milligram per liter. Okay, 14.6 if you remember is fine with me. So when you say saturation DO at 0 degrees, you will have the maximum DO dissolved in water. And you know that in tropical countries like India and all, our temperatures will never reach 0. Maybe there will be countries where that is there. So these are two very contradictory terms that we will be using. You can imagine in a place where the temperature is so cold, 0, because the temperature is low, the dissolved oxygen concentration is very high. But at that temperature, so low temperature, how many organisms will be active to do the degradation work? Understood? So that is a contradictory to the amount of DO present. But if you take a country like India, where at say in our winter times we may have very pleasant temperatures of say about 11 to 15 degrees, and at that time organisms are also more, though organisms become very active in the temperature range of 20 to 30 degrees. Okay, even at that temperature of 15 degrees, we will have a lot of active organisms and we will have sufficient DO. So one thing which I want you to keep in mind right now is at 0 degrees Celsius, we have the maximum saturation of 14.6 milligram per liter. And when it comes to about 30 degrees, the temperature, your DO drops to 7.63. So almost to half. This one small thing you can keep in mind, which will give you a very big reference. So whatever temperature people talk about in between, you may not be able to guess the actual or exact value. It's not needed also because there are calibrated graphs. But when you know that 0 degree temperature, you have 14.6, and at 30 degrees Celsius, your DO concentration comes to 7.63, then you know at least by interpolating with what value for a particular temperature your DO will be. Okay. So in this particular graph, never do the mistake, because I've had it happen, okay, of joining this like this, because this shape will come easily, DO graph. You memorize something and you just draw it like that. Then you make a big mistake there. Okay. So at the point where the wastewater is discharged, there is no need that the situation has to be saturation level. Understood? So you will have an called DO deficit based on the difference between the saturation DO and actual DO. Now, there is a major point in this, which is called as the critical point. That means the point at which your DO is dropping the most. Just go back to our previous figure. You saw that they are telling it's going to go to 0. This is an approximation. It may not happen that it will come to 0, but there will be an oxygen level where it has come to the critical level. So the major point of interest in your oxygen Sag curve is the point where minimum DO or the maximum deficit. Minimum DO will give maximum deficit, because deficit is difference between this. So maximum deficit or minimum DO is there. This maximum deficit point is called as the critical deficit, and we use DC for that. So the critical deficit point in the curve. So now you can see two other curves. So again, your zone of recovery and then clear water zone. So your graph is following the same pattern as what I was talking in the zones of pollution. Now you can see two other dotted lines which are mentioned here, that is called as the deoxygenation curve and the reoxygenation curve. So deoxygenation is the rate of oxygen removal which is happening, and reaeration is the regain of oxygen which is happening as your water gets clearer and clearer. So when the pollution load is discharged into the stream, the DO content of the stream goes on depleting. Okay, the depletion of DO content we call by the term deoxygenation, and the rate of deoxygenation depends on the amount of organic matter that is still remaining at a particular point of time based on the temperature of water. So deoxygenation, how much of oxygen is getting depleted at a particular time, depends on how much organic matter will be remaining at a particular time. That's also connected to your temperature. The variation of the DO content of the stream with respect to time is what is given by your deoxygenation curve. So normally all these three curves you write and explain together. Okay. So when they will usually ask you to explain the oxygen sag curve or the deoxygenation curve, you need to explain all this and then come to the conclusion here. Now, though the DO content of the stream is getting consumed, okay, atmospheric oxygen also will be dissolving to a certain extent, maybe not so much in the beginning because of all the pollution, but it will be getting dissolved because the stream may be passing, like there may be rocks in the stream. So the flow will go over that and drop, small hydraulic jump will be created. Whatever it is, there will be some reaeration happening. So even though there is some consumption of oxygen due to the BOD load, atmospheric oxygen is continuously getting into the water, and that is what is giving you your reaeration, or we can call this as reaeration curve also, or reoxygenation curve. But how much of reoxygenation or reaeration happens depends on the depth of water in the stream. Okay, so we know that if the depth of water in the stream is less, more oxygen will reach. The depth is too much, then the bottom layers and all, there will be a chance that oxygen dissolving and reaching the bottom layers becomes difficult. So it will be more in the case of shallow depth than in the case where you have streams with very large depth. Second is velocity of flow. Suppose your stream is flowing nicely with lot of rapids, lot of currents, definitely the reaeration will happen faster because the oxygen dissolution also will happen faster. At the same time, if you have a sluggish moving river or stream, then it is going to be very slow. Then it also depends on the oxygen deficit below the saturation level. So if your oxygen deficit is very much more, it will take more time for this reoxygenation to happen. It also depends on the temperature of water. Like I told you, warm waters will not hold DO. Okay, so if your temperature of the water is low, then the oxygen that is remaining as dissolved oxygen in your water, there are more chances of it to be in a higher level. So this is the oxygen sag curve. Please don't look at this and say, yeah, simple curve, very easy. It has to be understood perfectly, and then we are not doing it now, but I'm telling you, there is a Streeter-Phelps equation which has been derived from this, so that we are able to predict from a distance at this, say 2 kilometers down this point, what will be your BOD level in the liquid at that particular level, or in the water, which is the stream at that particular level. What is the DO deficit there? We will be able to calculate. And so this is very, very, very important for you to understand. Okay, I think these are things that we have looked at. Okay, the amount of resultant oxygen deflected can be obtained by algebraically adding the oxygen and the oxygenation curve. The resultant curve is the oxygen deficit curve, which we call as the saturation DO, and minus the actual DO. These two values, please put it into your head. I'm sorry, this should be degrees. Okay, 14.6 at 0 degrees, 7.63 at 30 degrees. Put it into your mind so that anytime you need to predict or assume a value, okay, you know, on an average, you will be able to get your value correctly without making a large variation. Okay, so that is very, very important. I think we have discussed all this. The deoxygenation curve, which shows the depletion of DO. Okay, the rate of deoxygenation depends on amount of organic matter that should be oxidized at a certain point of time. It also depends on the temperature. The variation of depletion of DO of the stream with time is depicted by the deoxygenation curve. The ordinates below the deoxygenation curve indicate the oxygen remaining. So this is the deoxygenation curve. Here, plenty of oxygen was there. Oxygen is getting used up, oxygen is getting used up, oxygen is getting used up. So it goes down, down, down. When the DO content of the stream is gradually consumed due to the BOD load, atmospheric supplies, oxygen is happening to the water, and that we call as the reaeration. We can use either reaeration term or reoxygenation term. Both of them are fine. Okay. Now we come to the first part. When we talked about this, we talked about dilution, and we said that if we are diluting, we will be mixing small volumes of waste into large volumes of water bodies. And I also told you examples how in Bombay High they send from the city of Bombay initially, they had a pipe which used to take this wastewater a little deep into the ocean there, Arabian Sea, and they used to let out. So, and we said that there are two methods by which dilution can be done. One was in water and the other was in land. So today the remaining, and then we looked at what are the possibilities or the problems that are associated with when you are putting the wastewater into a natural water body. We talked about zones of pollution and your reaeration, deoxygenation, oxygen Sag Curve, oxygen deficit, everything. So now I'm coming back to the two topics that we were discussing earlier. First, dilution into the sea. Okay, sometimes when you have to do, and this is done, even though sometimes the cities may have a good treatment facility, etc., there are unprecedented times when heavy rainfall, suppose you have a combined sewer, heavy rainfall, and everything enters into the combined sewer, and then the sewer is not able to hold everything. No point in taking all this to the treatment plant because the treatment plant will just collapse. So they will find an alternative to send it to the sea or ocean or whatever it is. The sewage should be disposed into the sea some distance away from the shore, because you know that these pollutants have got a lot of foaming and other materials, and sometimes if you try to leave it very close to the shore, all these things will come back with your tide onto the shore. It's like the solid waste they try to dispose into the sea. Okay, they will try to go take it via ships into the ocean and dump it on the seabed, but along with tides all these things come back, and then on the beaches and things like that, these things will come back. Similar things happen with this also. The outfall is the last section of your sewer pipe, should be designed such that there should be proper dilution of the waste with seawater before the waste comes back to the surface. So the pipes that we are laying are usually laid deep down so that we are not disposing the waste near the top surface of the sea where you have lot of tides. There are undercurrents, obviously, nobody can control that. But we try to leave it at the bottom so that whatever is rising, it gets a chance to mix with the water thoroughly before it comes to the surface. The sewage should be disposed of only during low tides. You know what all damage can be done by the tides. So for this purpose, tanks of large size should be constructed during high tides and they were released. There are different ways. Now they don't do tanks and all now. They will take a deep pipe underground. So while designing the position of the outfall, direction of wind velocity, direction of ocean currents should be considered. So a quick look back at what we were talking about as a dilution, method of dilution. So when you are discharging wastewater into large water bodies so that the quantity of waste, which is a little not a little, vastly less compared to the quantity of water, only then you will attempt this work. So keeping all these favorable conditions, such as your wastewater is fresh, not septic. I have used this word many times earlier, so I'm sure you people will understand. Fresh sewage, septic sewage. So when your wastewater is fresh, you opt for dilution in water. And where floating matters, large floating matters are probably removed from the wastewater before you dump them into the sea or other natural water bodies. Where the wastewater volume is very small in comparison to the quantity of water available in your disposal waters. And your disposal water, whether it is sea, river, etc., should be having a natural high dissolved oxygen. Okay, and when there is a possibility for good mixing of the two, the wastewater and the natural water, we will opt for this method. And major thing, where the water into which you are disposing is not a source of drinking water. Keeping in mind all these things, we will decide whether method of dilution is possible. Okay, now I have certain questions for people. Jeevan, are you there?
Yes, ma'am.
Jeevan, just tell me, what is oxygen deficit?
Oxygen deficit.
Yes. Google Guru will give the answer.
No, ma'am.
Then which Guru? So all this, what I'm talking, is vain, right? Okay, tell me what all I talked to you about today, till now.
The
Half an
oxygen
hour.
Sag Curve, ma'am.
What is oxygen Sag Curve? Did I use the word oxygen deficit when I was trying to explain it to you?
Yes, ma'am.
Then what is it? That's all I'm asking.
The TO DT DC.
Correct, Appa. What is it? Difference between?
Don't know.
Okay, then I told you to keep in mind certain value of DO at
Yes,
certain
ma'am.
temperatures. That can you tell me?
Yes, ma'am.
Yeah, tell me.
At,
These are important questions for you in your multiple choice exams that you will be giving. Understood?
Yes, ma'am.
So tell me.
At 0 degree saturation, 14.63 milligram per liter. Yes, ma'am.
Okay.
At
And
30 degree saturation, 7.63 milligram per liter, ma'am.
okay, very good. At least that you remembered. I'm happy. You can mute yourself. See, all of you, this value I'm trying to tell you to memorize so that certain conditions when not only to do problems in day-to-day life, okay, an approximate value you will be able to give for your DO based if you know the temperature of your water. Yeah, so please do not forget that. Next is Gaura. Gaurav, are you there? Janvi? Prajwal? Likith? So whoever has not answered right now, I will not be giving the attendance also. Soundarya. Upamanyu. So I'm sorry for these people. I will not be able to give the attendance because Subhashri is there.
Yes, ma'am.
Subhashri, I want to dispose my liquid wastewater into a water body. Okay.
Okay. Okay.
What are the things will I need to consider?
Ma'am, the source I'll consider, ma'am. From where it is. Is it from?
Can you repeat what you said?
Ma'am, the source, ma'am. Is it sewage water or?
Okay. We need to consider. It is sewage water. I'm telling it is sewage water. I want to use the method of dilution. So, what all things should I keep in mind for selecting a dilution can be done by what? Where can I put it for dilution?
Into the sea, ma'am. Dilution into sea.
Only sea? Can I make it a statement that dilution can be done only in sea?
No, ma'am.
In any water body. Understood? Are you able to hear me?
Yes, ma'am.
Okay. So I want to put it into water body. What all things should I consider?
Ma'am, it should be. Ma'am, it should be discharged deep into the sea, preferably 1 to 1.5 kilometers away from the shore, ma'am.
Okay.
Then the outfall should be designed in such a way that there should be proper dilution of waste with seawater before waste tries to come to the surface.
Agreed. Oh, you are reading out my slide. I don't want this. I asked a general question. Okay. Other than that,
it should not be a drinking source, ma'am.
it should not be a drinking source.
It should be put in deep enough for the sea, ma'am.
So that's about sea you're talking about.
The minimum,
In
yes,
terms of
ma'am, minimum depth.
volume of water that should be available. Is there a consideration for volume of water that should be available?
Yes, ma'am.
Okay. So that means the source or wherever you're putting the water into should have much more quantity or volume compared to the volume of sewage that I'm trying to dispose. Correct?
Yes, ma'am.
Also, the DO content should be more. It should have a good DO content so that even if I'm adding my waste into that, it will not deplete the DO completely to zero. Yeah.
Yes, ma'am.
So then we looked at dilution by sea, disposal this thing by sea into the sea. Now we can also see about what happens when disposal is done on land. So many of us would have heard of this term. We also have a psychological block when we say talk about sewage farming, because sewage farming is something that is being done by using, actually treated wastewater has to be used, but there are places where they normally try to use untreated waste also, and they grow vegetables, leafy greens, etc. And because of that, there is also you can mute. Subhash.
Ma'am, I have a doubt, ma'am.
Yes.
It's me. Is it okay if I ask, ma'am?
Ask.
Ma'am, we consider many factors here when we are disposing, ma'am.
I
Ma'am,
can't hear you clearly. Can you just speak a little slowly?
yes, ma'am. Is it audible, ma'am?
It's audible, but then it's like blurred. Like I can't make out what you're telling. Tell slowly.
Yes, ma'am.
Yeah.
Ma'am, you told when the sewer is full, we will think of disposing it. No, we consider many factors with respect to the water. Water body should be clean, volume should be more, and all that. How
Yes.
about the sewage, ma'am? Should we not consider it should not be any industrial waste?
No. That's what that. See, you got the point correctly. Thing is, we are actually not expected to put in untreated sewage into water bodies, and we have a regulation. Okay, there is a standard Central Pollution Control Board regulation that the BOD has to be brought down to certain level before you are allowed to put it on water, allowed to put it on land. Okay, so we are never supposed to discharge sewage into direct water bodies. This is the first point I told you in the first class when we started. Though we are talking about sewage being disposed, under unavoidable circumstances, yes, it is being done. You can practically see it with your eyes if you go to the Vrishbhavati treatment plant, which is handling the lot of wastewater from Rajarajeshwari area, Pina industrial area, etc. Everything is coming. They treat it and then they put the treated effluent water into the Vrishbhavati river. But there is a by-channel. What that channel does, rainy season, you are getting water from everywhere coming. They cannot handle it in their treatment plant. Their treatment plant is 120 MLD capacity. Okay. If excess more water is coming, what are they supposed to do? Can this water be blocked anywhere and kept? No. So what they will do? They will have a bypass here and some amount of this will enter. Got it? Is it Yaksha?
Yes, ma'am.
Okay.
No.
So, Yaksha, by true norms, we are not expected to put untreated sewage. Now, regulations are in place, but these things were being done. Even now, without knowledge, people are doing it. That's why your lakes are getting exposed to this much of pollution. Treated waste, if you are putting, this problem shouldn't be there. Clear? Yes. So what we are talking about now is where to dispose. Okay. So where to dispose, there is only two methods. You can either use it up for your irrigation and whatever it is on land. That's what we are coming to now. Or you have to put it into a water body and get mixed and take it away. Did you understand?
Yes, ma'am. I got it. Thank you, ma'am.
Okay. So it is a consideration. Your waste has to be treated to a level. We will come to regulations of this later. Understood? In that, it will be very clear. If we have to put it into a water body, this is it. But that is all with respect to regulation. Sometimes these are bypassed. But selecting a water body itself, now I have treated waste, but my water body is so bad. Into that again, if I'm going to put this, it's not going to help in any way. Understood? So if a dilution method is to be used, what are the considerations that we should look at? Yeah, we are not talking about the input quality of the waste at all here. Yeah.
Okay. Thank you. Sorry. Thank you.
Okay. So now we are coming back to what we were talking about, land. So what happened is the sewage farming, initially when people found out, especially this was this started in a big scale. At one time there was maybe you people were too small. Our younger days and all, people they used to be very reluctant to use small onions grown in certain places, telling that this is grown in sewage farming. Sewage, as you all know, contain a lot of nutrients, especially phosphates and nitrates. Nitrogen comes from your organic waste. When it gets this thing, we all use some amount of detergents and things like that, which has got phosphates. Okay, most of our detergents have a lot of phosphates in them. Suppose agricultural runoff is mixing with that, there is going to be more phosphates because it's coming from your fertilizers. So lot of these nutrients which are present in the wastewater is very good for plant growth, and your plants will grow pretty well. So people started using this as part of sewage farming. So that was even with untreated waste, they were doing it. But nowadays, they are encouraging because you are able to treat the waste to a very good degree so that the BOD level is very less. And if you are making use of that water, the benefit of nutrients in the water is there. Plus, at the same time, fresh water can be avoided from being consumed for purposes like this. So there is an added advantage. So when wastewater, that's why everywhere you see raw or treated. Some people do tend to use the raw sewage also. So can be disposed of on land, okay, where they are basically used for 3 broad purposes. They call it as broad irrigation or sewage farming, rapid infiltration, or overland runoff. Now, what is rapid infiltration? I think all of you have studied about rainwater harvesting or heard about rainwater harvesting. I'm sure you are the batch that went to the Jayanagar rainwater harvesting unit. Yes? Did you people go?
Yes, madam.
Okay, so rainwater harvesting, when we say from rooftops, paved areas and all, happens in cities. But in rural areas, there is a lot of rainwater that can be harvested from agricultural land. And even in cities, the treated wastewater, if there is no way that you can use it, you can use it for what is called as groundwater recharge. So this water has been treated to so much degree that it is not having very high polluting capacity. Now, so much of wastewater is there. You don't want to use it for agriculture. You don't want to use it for your landscaping, nowhere. Then the next best thing that you can do with it is allow it to reach your groundwater table. And you know all the series of layers of soil, and you will make percolation pits also. We will talk about this on a later stage. If you are filtering this water through a layer of aggregates, gravel, sand, etc., and then allowing it to seep through the ground, as it filters through the ground, all the remaining contaminants will get trapped in your media of soil and sand, and this water will get a chance to mix with groundwater. Understood? And then there is the overland runoff, which is nothing but what I was trying to talk to you. From farmland or land, whatever falls, that can be removed. So the first 2 processes depends upon the percolating water downward through the soil, so that the infiltration and percolation capacity of the land can be made use of. So for this, we have best methods of sewage farming and infiltration that are being used. I have 2 pics here before I stop the class. I think it can be seen here. You can see, suppose you are growing crops. Okay, 2 best methods are sprinkler method. Sprinklers you have seen in the college also. And you know, sprinklers put fine droplets on the soil. So if you are, all of us have experienced this. Most of you would have plants at home. Somebody asks you to pour water. Okay, to water the plants today, you will find the easy method. You will take a large cup of water and try to dump. Little of it will fall into the pot. Most of it you will have outside the pot. Okay, but at the same time, if you have a spray can, what is spray can? Okay, if you use that, even if you have put only half glass of water, that half glass will go correctly into the plant, because it will, same thing is what is shown in your first case. Okay, and you can see that when water. So this is the recharging that's happening. Okay, rapid infiltration. You can allow it to reach into the underground soil. But there are some types, sometimes it can be runoff, which will just flow through the surface and it will get collected in runoff pits or runoff channels. Okay, but that water, as it is passing, it will, some amount of it will percolate into the ground, and that can be used by your crops. So these are the different methods. As of now, we will stop the class with this. But I'm really unhappy is you people need to listen to the class instead of just logging in and then disappear. When I ask questions, if I don't get a response, today all those people will not be getting attendance who did not answer. Don't even reply. Yeah.